Okay, so let's get started. So today's plan is to finish these decision trees that we started last time and then start talking about linear models and classification and regression with linear models. That would be a long lecture, so we won't finish it. It would be great to finish the first part, so linear regression part, but let's see. So we saw decision trees. So I'm just going through it quickly. So we saw KNNs in the first lecture, but then here we are introducing some other method. This is called decision trees, which looks more like how maybe humans make decisions. So one issue is that if you have a decision tree, making decisions is easy. So we basically compare the attributes with the values in the on a tree, and then we just follow that. So basically, we follow, check the width, whether it's larger than some threshold or not. The issue with decision trees is that, well, how to learn them, and then learning them basically depends on, or can be divided in two main components. One component is first, suppose we know the structure of decision tree, what should we do in each of the decision regions or in each of the regions? And so that's not difficult. So we have these things that if we are in the case of classification, it's getting there soon, yes. So in case of classification, a reasonable thing to do is to basically choose the do a majority vote and decide on a class with most of the labels there. And as the question, it was a good question that, okay, so why do we need to have enough points there? The reason is that if you want to be confident that, say, this region is like orange or lemon, it would be great if we have more than on one or two samples. But then the other question about decision trees is how to find the structure of the decision tree. So the idea here is that we want to go for simple trees. And simple is a kind of vague term. One way to define it is saying that finding the smallest decision tree which correctly classifies all the training set. But this problem is computationally expensive. It's NP-complete. So instead, we do some kind of greedy algorithm or greedy heuristic to construct the tree. This would not be optimal, but it might work reasonably well in practice. So now the question, of course, is that, so these greedy algorithms are based on splitting the tree based on some best attribute. So they decide whether, say, width or height is the best attribute to make the split and then grow the tree that way. But then the question is, how should we define best? And here we use a notion of gain that basically we say that gain is defined based on some change in some criteria before and after a split. So now the question is that what is the criteria? And there are different types of heuristics here. One is based on the accuracy. So, and then we define accuracy gain, which accuracy basically means that before the split, like here, and after a split, how much the accuracy changes. And then we talked about how it's defined. So essentially, we have this misclassification loss or rate, which is basically how many errors we make if we say that in region it should be orange, but there are a few lemons in that region. So we have this, after the split, this would be our misclassification rate. Before that, it would be this one. But then, and then the difference would be our accuracy gain. So, but then I argued that, well, this is one criteria, but then this may not be the best criteria, or at least the most intuitive one always, because here we have this split, which if we do this decision here and then split based on that width and this threshold, we get to a one region, which we are very confident, we are very certain about the true label. And intuitively, this may sound a good split, because by doing that split, we don't need to worry about that region anymore. And now, I mean, for the next split, we can think about how to split this region later. But at least for this one, we don't need to be worried about the quality of our decision, essentially. But then the problem here is that with this type of split, the accuracy gain is. So here we've reduced the uncertainty about whether food is lemon or not, but this criteria doesn't show that that was a good split. So now we want to talk about uncertainty as a criteria. Use uncertainty as a criteria and then define the gain based on how much we change the uncertainty before and after split. So now the idea is that, okay, the question is that how to define uncertainty. And I think I stopped here last time. Now I want to talk about some basics of information theory, which is a framework, mathematical framework that allows us to talk about uncertainty. Any questions so far? Okay, how many of you know about information theory? Had a course on it or in one course? Okay, so a little bit, yeah. And we only need a little bit. So there is a whole course on it, in, I guess at ECE. But we just need basically the first few concepts. Okay, so suppose we have a coin, and if we flip the coin and we get a sequence of zeros and one. So we get 0, 0, 0, 1, 0, 0, 0. So this is for the first coin. So this is the first sequence. And then maybe I have a bit of echo. Okay, my voice is still okay, right? I think on your side. I think I had some echo before. Okay, so that's the first sequence, and then second sequence is 0, 1, 0, 1, 0, 1, 1, 1, 0. So we have these two sequences, and now which each of them correspond to two different coins, coin 1 and coin 2. So I ask you which coin is more, how certain you would be if, like, I flip the coin again and I ask you what would be the outcome. Okay, so maybe first of all, we start with the first sequence. So what is the next coin here? Yeah, so it is most likely to be 0. And you are kind of certain about that, right? So, I hear a bit of echo here. Sorry about that. But I'm worried that in recording it would be problematic. Yes. Maybe it's actually from. Okay, sorry. Okay, so, but what about the second coin? Do you agree that you are less certain about what is the next outcome here? It can be 0 or 1. Now, so this is if you kind of measure the number of zeros and 1 in this sequence. The first sequence has 16 zeros and 2 1s, but the other one is 8 and 10. So you see that the probability of one of these happening for the first sequence is kind of very unequal. Like one of them is concentrated on probably being 0 coin. The other one, both of them, the probabilities are kind of, or the number of occurrences are more or less the same. So we want to use this kind of, make this intuition to define some notion of uncertainty about it. Okay, so we have this notion of entropy, which is a measure of surprise that we have in seeing a sequence or any observation from random variable. And explicitly, it is talking about what is the expected surprise, which defines that how uncertain we are when we see a value of a draw from a distribution. And the way it is defined is like this, that entropy of random variable x, so x is the random variable, and h of x is the entropy of it, is defined as the expectation or minus of the expectation of log of p of x. Or we can expand it, we can have it like this would be minus of p of x of log of p of x. So this is the definition of entropy, and maybe we can see how it works if we do the calculations. So if we do the calculations here for the coin from the sequences from the previous slide, so we get that with some probability, like probability 8/9, we have this log of 8/9, and then plus 1/9 of log of 1/9. So this gives a entropy value of half, approximately. If we do the calculation for the other one, we get a sequence of 0.99. So this value is larger, and basically it's saying that we are more uncertain about this random value. So entropy can be interpreted as the average information content of each observation. And if the value is higher, it means that it has more information. And then the unit of entropy is called bits, which is the same bits that we have in computer science, like bits and bytes. And maybe to have a better understanding of it, we can think of it as if we have a fair coin, which the probability of both sides is half, the entropy of it would be 1 bit. Because in that case, if we do the calculations, the value that we get would be 1, the entropy of it, and the information that revealing what 1 bit gives you is essentially just 1 bit of information, whether that's 0 or 1. But then if the coin is very biased, it's always 1, so you don't get much information from 1 flip of the coin, because you know that with, say, high probability, you get a value of 1, essentially. So this is the notion of entropy. And so let's just do maybe some kind of exercises. Maybe I just move through them quickly and let you think about them. But so, okay, maybe one question is that what is the entropy of a uniform distribution over 1 to capital N? So if we have a random variable that can take values between 1 to N, but then, and the probability of them is uniform. So what would be the value? Log N, right? Yeah, okay, so that's good. So that would be log N. So we have, what is the probability? So we have summation over I equal to 1 to N, each of them 1N of log 1 over N. There's a minus there too. So we have N times log of, log of 1 over N. So let's see. 1 over n. So this goes away, and then we will have minus log of 1 over n, which would be log n. And this is a base 2. Yes?
Is n something you don't know?
No, this is like, no, here it is assumed you know n, and I'm just asking in this specific question, what would be entropy?
I thought it would be entropy to be 1 because 1 draw doesn't actually tell you anything about where the next draw is coming from, the value of the next draw. If you only know.
Right. That's okay. So suppose n was 2. So in that case, it would be log of 2, which is in base 2, it would be equal to 1. So if you have a random variable that can take 2 values, 0, say, if n is equal to 2, the set is equal to 1 and 2, or maybe I write it actually similar to what. So here n is equal to 2, then this computation shows that one uniform sample from these 2 possibilities gives 1 bit of information as what we had before. So that would be log of 2 in base 2, which is 1, right? But now suppose your random variable takes 3 and 4. So here, basically what I'm saying is that this random variable, you have more uncertainty. One draw of it, the information that gives you is more than just one coin that has only 2 possibilities. Or you can think of it another way, maybe. This can actually be seen as you have 2 different coins that you flip together. 2 unbiased coins that you flip together, because 2 coins means 2 bits, or each coin means 1 bit, then 2 coins mean 2 bits, which is compatible with what we have. Okay, so. I don't know why I have a little bit of feedback. Do you hear any feedback on your side? People on Zoom? Okay, no feedback, thanks. Okay, so, okay, let's try another kind of case. So what is the distribution of entropy of a distribution that is concentrated in one of the outcomes? So P, the probability of each of the possibilities is like this. It would be 1 for one of them, and then 0 probability for all of them. So what would be the entropy of it? 0. Why? Or what intuitively why? Sorry, say again. Yes, exactly. So the answer is that because we know everything about that random variable, it's always going to be the same thing as before. So that's the case. That's the reason. So that's the case. And then you can compute the distribution. So, well, this is not going to be distribution. This was supposed to be the entropy. Entropy of a distribution of a Bernoulli random variable with probability of 1 being P and 0 being 1 minus P. So this is Bernoulli distribution is like the case of fair or unbiased coin is an example of Bernoulli distribution. And now I'm just saying that what if it wasn't fair or unbiased, but there's a probability of P and 1 minus P there. So if you draw it or compute it, and I guess it's a good exercise to do it yourself, you see that the behavior is like this. So this is the P value, and this is the entropy. And you see that when point is the probability P is equal to 0.5, we have the maximum entropy of 1 bit. But then as P becomes 0, close to 0, close to 1, the entropy goes down because we become more certain about that random value. Okay, is this clear? Perfect. Okay, so in general, I think what we have is that if a random variable has a uniform like distribution, or uniform or almost uniform, then it has a higher entropy. Or if we compute, which another way of saying is that if we compute its histogram of random variable, the histogram is more or less flat. So that would be high entropy case. And this basically means that values that is sampled from that random variable would be less predictable. On the other hand, if the distribution has peaks and valleys, so basically if it looks like, say, instead of kind of being like this, then that distribution has less entropy because we are certain that with high probability we are falling in this region. And the value sampled from it are more predictable. So this is basically what we have. Okay, so we can talk about the entropy of a joint random variable. There's no real difference in computation of everything. We just need to talk about joint distributions. So as an example, suppose we have the set that X can take the value of raining and not raining, and Y can take value of cloudy or not cloudy. So each of them is a binary value or binary random variable, but they have a relationship with each other. They're dependent on each other. So this table basically shows what is the probability of each of the possibilities. Say if it's, say, cloudy and raining, the probability is 24/100, 24%. But raining and not cloudy, it will be very unlikely events. So something happened, which is kind of strange. But then, say, non-raining, not raining, and cloudy 25, not cloudy, not raining is 50. And if we do the calculation here, which would be the same as before, except that summation, this probability or expectation is over the joint over the distribution of this joint random variable. So it will be P of X and Y and the log of P of X and Y. And if we do the computation, we get something like 1.56 bits of information. Okay, so what situation we would get 2 bits of information here? RP 0.25, yes. I think that would be the case. Yes. Okay, so basically, if both of random variables, for example, are, we will see it soon, but if the random variables are, each of them are uniform, and also they are independent from each other, we get that probability that each of them gives 1 bit of information. Okay, so that's good. Okay, now we can talk about conditional entropy too, which basically says that how much uncertainty we would have if we know the value of one of the random values. First, I talk about the case that we know that, say, we want to compute the entropy of Y, the cloudiness, given that we know that it is raining already. So I specified X, there is no randomness in X. I'll tell you what is X actually is. It is raining. So the computation of it is straightforward. We just need to use the conditional probabilities. So entropy of Y, conditional X being raining, is the probability of Y when X is equal to, or X is raining. And the same for the log term. And if we do the computation, we get that it's 0.24 bits. And it's good for you to go through this computation and see whether it's accurate or not. And here, I mean, in order to compute this thing, we need to be able to compute these conditional probabilities, right? But in order to compute these conditional probabilities, we can essentially use this rule, Bayes' rule. So we know P of X and Y. We need to have P of X, but P of X is essentially marginalization of Y out. So we can do all these computations. So this is the idea of conditional entropy when X is some specific value. Yes, there is a question.
Yeah, so if you know that it's raining, does that automatically reduce the entropy? Or?
Yes, I believe your knowledge of something reduces your entropy. But compared to entropy of joints, you mean?
Compared to entropy of just Y.
Just Y.
Y versus Y.
Okay, so I guess we are comparing h of Y versus h of Y, X being some specific value, right? That's a good question. I believe so, but I'm not 100% sure. But I believe that will be the case. Yeah, having information about some random variable reduces your entropy of about it.
But what if the Y given X is raining has a lot of uncertainty, but Y given X is not raining are almost certain? But in this case, maybe like HY given X equals raining is even larger.
Okay, yeah, I guess I see what you're saying, but I'm not sure if that can define the properties that way, but I'm not 100% sure. I should check to see whether that is true or not. For one specific choice of X. I think we have results that if you compare this versus X, like value of X, but not specific value, you see the definition on next slide, that reduces the entropy. But one specific choice, I'm not 100% sure. So I have some entropy here. Yeah, so I guess there was a comment that h of Y condition X is not larger than h of Y. That's true. But I guess here the question is that if X is one particular choice of X, there's no randomness over X, what happens in that case? I guess you can show it, but let me think about this. So there's also a question that how to calculate P of X and Y. P of X and Y is this table. So this table is P of X and Y. So P of, say, cloudy and rainy is 24 over 100. Okay. So now we have this expected other concept, which is we have conditional entropy, but we take expectation over the possible values of X. It is not raining, but we consider the probability of being raining or not. So here, essentially, we are computing, it would be h of X, Y condition X, which would be entropy of Y when X comes from this distribution. So we consider the probability of each possible X, which we can write it again like as P of X, h of Y condition X being one particular X, which we had in the previous page. And then if you expand this, you get essentially to something like this, that it would be expectation of X and Y coming from this joint distribution of log of P of Y conditional X. So that would be conditional entropy. So here, what's the entropy of, basically, yes, so we want to compute h of Y, entropy of cloudiness, given the knowledge of whether or not it is raining. And if we compute it, well, in order to compute it, first we need to compute this probability of being cloudy conditional raining and not conditional not raining. And then we consider the probability of each of P of X's, which we can compute from this table. And then the result is 0.75 if you do it. Okay, so there are some useful properties. Entropy has some useful properties that it's good to know. So one is that entropy is always non-negative. The minimum value that it may take is 0, which is when there is no uncertainty about that random value. And then entropy has a chain rule, which basically says that entropy of joint of X and Y can be written as entropy of X condition and Y plus entropy of Y, or entropy of Y condition X plus entropy of X. So how much we are uncertain about X plus how much we are uncertain about Y given the knowledge of X, or vice versa. The other thing is that if X and Y are two independent random variables, so they don't have any dependency on each other, the entropy, then the knowledge of one of them does not give us any information about the other one. So what we have is that entropy of Y condition X, if they're independent, is equal to entropy of Y. And also vice versa. Entropy of X condition of Y would be entropy of X. I guess we can see that from this chain rule and X and Y, this other property about the independence, that if X and Y are independent, then entropy of the joint value of them is entropy of each of them. So this is like, I give you two coins that are independent, so there's no connection, physical connection between them. I ask you what would be the entropy of flipping both of them at the same time. That entropy would be the same as entropy of flipping one of them plus entropy of the other. But if they were somehow connected to each other, so there's a dependency on each other, then that would not be the case in general. Okay. Another property here is that, maybe use a different color, is that but Y tells everything about random variable Y. So if you want to compute entropy of Y condition of Y, there's no uncertainty about it because you know Y already. So if I tell you what Y is, there's no uncertainty left. So, but if we know X, we can only decrease uncertainty about Y. So this is, I guess, one of the things that mentioned already in the chat, that entropy of Y condition X is not larger than H of Y. So this is another property of them. And it's good exercise to try to verify them. They are not difficult. They just need to use properties of random variables. Like essentially you need to use something like this a few times for conditional, to convert conditionals to joint or vice versa, and use properties of log, which is log of A and times B, it's log of A plus log of B. And you may need to do some kind of marginalization. I think most of them, the proof is that simple. This one, H is always non-negative. I think that's a bit less trivial. But I actually may ask you to prove it in a homework that I'm going to release tonight. So, but I'm going to give you hints how to do it. I get back to this figure later. Any questions so far? Yes.
The proof of the chain rule is not very clear. Why it's
the proof of it?
Yeah.
Well, I haven't really proved. Or do you mean the proof of it, or why it is true?
Isn't that times hx? Oh, it's long, so it's fast. Okay.
Yeah, so the question, just to repeat, is that this chain rule is not very clear and how it's proved. And I guess one answer here is that you can just use Bayes' rule to prove it. Yes. Sorry, the H is negative. It's Jensen, yes. Yes. So it's Jensen's inequality, but Jensen's inequality, you need to prove it, or you need to know it's kind of like less elementary compared to these things. So the questions that, or the comment was that for the non-negativity, you just need to use Jensen's inequality to prove it, which is true, but Jensen's inequality kind of, it's less elementary than elementary properties of probability distributions, for example, or log. Okay. So there is this other concept which is called information gain or mutual information of y and x, which is basically trying to answer or quantify this question: that how much information about, say, cloudiness do we get by discovering whether it's raining or not? So it is defined as, say, if mutual information on x and y, or information gain of y condition x, is entropy of y minus entropy of y condition x. So the first term, this one, is entropy of y when we don't know anything about the other random variable, but the knowledge of other random variable x changes our uncertainty about y. And this is that uncertainty. The difference between this uncertainty before and after knowledge of y is called mutual information or information gain. So if we compute it for our case, the value would be 0.25. So some properties of it is that if x is completely uninformative about y, the mutual information or information gain would be 0. If it is completely informative about y, then mutual information or information gain would be entropy of y. And yeah, so basically, this is kind of a good way, or kind of to suggest that information gain might be a good criteria for us for the purpose of deciding whether we want to split a tree or not. Because this idea that how much uncertainty changes before and after knowledge about something is exactly something that we want to have when we wanted to decide whether to split or not. So if you recall, we start from the point that we said that uncertainty, we want to see how much our uncertainty changes to use it as a heuristic to decide to split or not. And this information gain has exactly that same property. That's saying that knowledge that the split is like this, how much it changes our uncertainty. Okay, so, I forgot to talk about this. So there is this kind of picture that might help visualize the relation between these entropies or entropy-related concept. This is a bit, it may need a little bit of thinking what actually it's doing, but here at the top layer, I have joint entropy of each of random variables, x and y. Then we have the concept of entropy of x and entropy of y. So in some sense, this is like showing a smaller region compared to all of it, kind of indicating that there's less information in just that part of it. It is not exactly a subset relationship because, but I'm just showing it this way. And then we have this concept of conditional entropies, that H condition Y. So for example, if I know some knowledge about Y, how much entropy would be left for us? And say we compare H to H of X condition of Y, we see that entropy is kind of become smaller. And the same for here, like if I have the knowledge about X, this entropy is going to be decreased. And then what is kind of left between them, that would be the mutual information. So we can have this relation. I guess most of this relationship can be kind of summarized in this figure if you want to remember that. Say, for example, so for example, h of x plus h of y conditional x, we see that this kind of, if we add to both to each other, we get entropy of joint value, which is essentially the joint, this chain rule that we had, and other properties that I talked about, or at least some of them. Okay. Any questions so far on the entropy and information theory? 20 minutes of talk, 20, 30 minutes of information. Yes. This one?
For the first one, H is always negative, not negative, sorry. Can't we just say that since it's the negative of the log, is the summation of the negative of the log, and the log will always be negative since it's the log of probability, which is less than 1. So it is always negative, negative times negative.
Yeah, so yeah, I'm not saying that this is difficult to prove. But you're saying that, okay, so P of X, log of P of X, yeah, I think that would be enough, I think. Yes, I guess for proving, so basically you're saying, okay, so the question was that since the log of P is always negative, because P is always between 0 and 1, so it's always negative, and P of X's are positive, so multiplying it would be always negative, and then we have a negative before that, so everything would be fine. Yes, sure, yes. Yeah, because Jensen, you don't need Jensen to prove that. Okay, what do you need Jensen? Maybe Jensen is for proof of, okay, maybe it's the proof of the KL divergence is non-negative, not entropy, which I haven't defined it. But yes, okay, yeah, I guess the proof is even simple, it's elementary, as you said. Okay, so there's a question that whether I of X and Y is the same as H of X and Y. No, they're kind of defined differently. But then there's another question that whether H I of X and Y is the same as I of Y and X, and that's true. And the question is, what's the difference between I of X and Y, mutual information, and information gain of X and Y? There's no difference, they're the same. So I guess it's just, I think in the context of information, in decision trees, people talk about information gain because it sounds like the gain is similar to what we talked before, but in information theory, I think people more talk about mutual information. Okay, so let's go back to decision trees. So here, now the question, let's go back to the original or one of the figures that we had before, which is we want to decide on where to split. And let's talk about the, previously we talked about the change in the accuracy as a measure, but that change of accuracy was not very good for this particular case because the value of accuracy gain was essentially 0. And then we talked about, let's talk about uncertainty here because here our uncertainty should decrease a lot. So the way we can, now what we want to do is use information gain or mutual information as the criteria to decide whether we want to split or not. Okay, so let's see, let's Y be a random variable denoting whether something is lemon or orange. And then B would be a random variable denoting whether left or right split is taken. So whether we are left one or right one. And then we treat counts as probabilities. So if you have, for example, here, we have 50 total, but 50 lemons, 0 oranges. So the probability here would be being lemon is 50 over 50, but here the probability of being lemon is 50 over 50 plus 49, right? And the same here, like 100 over 100 plus 49. So first we compute the root entropy, entropy of being something is lemon or orange, when we don't know any knowledge about, when we are at the root. So there is no condition there. And if we do the computation, it would be like minus 49 over 149 of log of that value, minus log of 100 over 149 of log of that value. And we get a value close to 0.91. Okay, so that's the entropy on how much uncertainty we have at the roots. But now we compute the entropies of the leaves after the split, which depends on whether we take the left split or we take the left region or right region. So entropy would be B of, when we choose the left side, the entropy would be 0, right? Because here, there is no, here in this case, there is no uncertainty about the random variable. It is always lemon. But then in the other case, when we are going right, then the entropy would be close to 1 because 50 and 49 is almost like this, equal these probabilities. And if we do the calculation of information gain over this split, so information gain of lemon or orange, condition on the choice of splits, we do the calculations and we get some value which is like 0.24, which is larger than 0. So this is basically showing how much information gain we have. So, okay, so I guess there's a question that how do you compute probability of being left or right in the chat. So here basically you use the how many lemons and oranges in each region. So here there are a total of 50. Here a total of 99. So that would be the probability of each of them, like 50 divided by 149 and vice versa. I guess this is shown here, like 1/3 and 2/3. Okay. So is this clear, the procedure, how we use information gain to decide on a split? More or less. Yes.
What's a good estimate for value for information gain? So we have there 0.24.
Yes.
What is a good reference value?
So the question is that what is a good reference value for this value of information gain, right? So so here the choice is that choose the split that has the most information gain. So this is one split. You could choose. There could be many other splits, and like 10 other splits, and you compute all the information gains for them and choose the maximum one. So there's no necessarily a good value or not. You just pick the one which has the most information gain. So yes, so at each, okay, so the construction of decision trees can, oh yes, there's a question, sorry.
So in the previous slide, we're still not deciding, right? We're just seeing how much of gain we're getting this scenario, but it doesn't mean this is the scenario we want. And neither we are deciding that it's good or it's bad because it's 0.24. We need to compare it with the other.
Yes, exactly. So the question is that this description on this slide is not about deciding what split to take. It is just a computation of information gain, and that's true. But we use it to choose the one that has the maximum. Okay, so basically, the way that we construct the decision tree is that at each level, we must choose which variable to split and possibly where to split it. So which variable here in this case is that whether it is width or height. And then the where to split basically means what would be that value. So maybe actually I had something before that might help. Okay, here what we had was the discussion of the change in accuracy gain. But to see what is happening here is that the question is which variable we should choose to split, like width or height. So for example, we choose width and what value to take for splitting. So one value is this point that defines that split. Another value is like 8.5, I don't know. This would be another value. And you could think about many other possibilities, right? So you have a lot of different possible choice for splits. This is on the width axis, but you can also do a lot for the height axis. And then you essentially do these splits and compute the information gain, and then choose the one that has the maximum information gain as your split. This is exactly the same as what we have here, except that here our criteria would be accuracy gain instead of information gain. But I wanted to talk a little bit about entropy, and information gain also is a good criteria. So that's another criteria that we have. But these are not the only criteria. There's other criteria that are used for similar purpose. Okay, so let's see. Okay, so there's a question of how do you choose where to split where the value is continuous? Do you form a discrete grid and compute information gain for each split? That's one way. But another thing is that maybe I actually try to draw it here. So if this is this kind of the grid, and suppose our information, our data points are these three. So these are continuous values, but we have 3 data points. So the possible points for a split, I mean, we can choose infinite number of points, right? But it is enough to just to choose the splits at data points, because any changes by that doesn't change any of the criteria, like information gain. Why? Because the way we relate the splits to probabilities, just counting how many, say, oranges on the left side and how many oranges on the right side. If I just move this a little bit value here before reaching another data point, the number of points on the left side and right side does not change. So essentially, I need to do n times number of data points type of split for each attribute. I mean, there might be more, well, I'm sure there are more computationally efficient ways, but at least this reduces infinite number of possibilities to finite number of possibilities. Okay, so yeah, so this is decision tree construction algorithm is simple, greedy, recursive approach that starts with a simple empty decision tree and all the training data sets, but then split on the most informative attribute using information gain, and then partition data set based on that and do it recursively. Yes, there's.
We have seen 2 measures here. Like we focus on using entropy or information gain, but we also saw accuracy as a possibility.
Right. Yeah.
Would there be any advantage of using like a convex measure? So we have just a convex optimization problem instead of going over all the options and doing it carefully?
I guess you can.
Just like making the optimization problem easier.
Okay, so let me try to understand. So what do you optimize on?
that would be the question. Like, if there is another measure, another metric that is useful, that makes optimization easier. And we don't need to go over all the options.
Okay, so the question is whether it is possible to have used some other criteria that we can do optimization over, and that gives us the splitting point. I'm not sure. I mean, you can combine these measures, say, instead of information gain or accuracy gain, set half of these things. But that doesn't give any answer. It's not answer to your question that maybe we can, I mean, you can think of it learning the splitting rule or this gain that we use that leads to better performance. I'm not sure that has been done or not, but I think it is possible to optimize that. But these criteria are not computationally difficult to do, because with proper data structure, you can do computation order of number of your data points. Yes, there's.
So we would basically be, so let's say we have let's say our input, it's like a 10, or yeah, the dimension of the image. We basically be looking for, like, for each of those 10, you want to see what is the best, like, what's the best splitting point we can do on that specific parameter and pick one of those?
Yes, so the comment was that if, say, we have 10 dimensional input, whether we have to go through all 10 dimensions to see which one has the best split, right?
Yeah.
So yes, that's true. Like if you have 10 dimensional variable, and say 1,000 data points, so it would be 10 times 1,000 choices, possible choices for each point of the node of the tree when you want to expand.
So would we split on a data point, or would we look for some continuous value? Like, let's say in this example, maybe put like put the line halfway between the 2 points.
So there would be okay. So I think there would be different ways to do it. So it's not one specific algorithm, and so the basic thing is just put it at these data points, or just before the data point. But then you can argue that maybe between 2 points would be more reasonable partitions or not. I'm sure people have done research on it, but I can't give it kind of comment.
You have enough data points, putting it on the point is probably faster, rather than trying to like put it on 8 points, probably faster than
So yes, the kind of comment is that whether we should put it between the points or on the points, and then the comment was that if you put it on the points, might be faster computationally. I think it doesn't matter much. I mean, if you know 2 points, finding the between point here, for example, between these 2 points is not much different computationally from just putting it at that point. But I should say that, and I'm going to briefly talk about it, like there are a lot of, this is the basic thing, but there are a lot of algorithms how to do it faster. Because if you have 10 dimension, 1,000 data points, it's already computationally seems to be expensive. But there are a lot of nice data structures, and people have done a lot of research how to do it efficiently, maybe approximately, which we are not going to talk about it. But decision trees have been there for a while, so you can expect all sorts of things have been thought about them or studied about them. And yeah, yes.
The only difference that would be visually more pleasant, right? If we decide to plot the decision boundary between halfway instead of the point itself.
So the comment.
Would it make any difference in practice in the decision tree itself? Because it's not adding more points or like removing any points. But it would be visually more pleasant if we draw the graph just like we did before we draw into the boundary.
So the question is that, or comment is that it would be only visually more pleasing if you put the splitting point between the points instead of just at point. On the training set, yes, but then you can argue that what would lead to better generalization? Should I just, like, if there is, okay, so I guess in this example, again, I use a different color. So if I want to split, which one is better to split? Like here, if I only have 3 data points or something in between, then you may argue that, well, if I have only 3 data points, why should I be very close to this one? Why shouldn't I give some enough gap or margin between them? I don't know if there is any theoretical results about saying that which one is better or not. I'm not sure. But at least I can see that as a possible argument that another choices might be better. Okay, so let's see. Some questions here, I guess So the split threshold is based on the training data. Yes, that's true. How do you find the most informative attribute using information gain? So you have a for loop essentially go over all possible attributes. So yeah, suppose you have attributes. Yeah, attribute 1, 2, 3, width and height, for example. You check information gain for attribute width for all possible splitting threshold, and then you check the computer information gain for height for all possible values of height, and then choose among them. Do we need to go through each point? In the scheme that I described, yes, but if you want to do it computationally faster, maybe you can do it, but just going to a subset of points, but then your split would be suboptimal. But I mean, the thing is that this is a greedy algorithm anyway, so there's no guarantee on optimality. So if you lose some optimality in choice of split, that's okay, because anyway, you are not going for optimal. Do we always split the region into 2 regions? So in the way that I described, yes. But I think you can think about other ways, like instead of binary trees, use something that is like, it's not a binary tree. You have more classes. Okay, so let me go forward, try to finish this lecture. Okay, so let's going back to our example. You read this. It is just doing a computation of how information gain would be, doesn't matter. Okay, so there is this question of which tree is better. And usually here the idea is that, so one tree is much smaller and the other tree is much larger. So usually we prefer to have a tree which is as small as possible, but can describe data well enough. So if it's too small, then it needs, so it shouldn't be too small, because if it's too small, it may not give good distinction or wouldn't have a good, say, classification error on training set. And it wouldn't generalize well to real case. Say, on the extreme case, suppose you only have a root without any splitting. That's a very small tree, which doesn't have a very good classification performance. But then it shouldn't be too large, because if it is too large, it starts overfitting the data points. So here we need to have enough samples in each region to confidently determine the output. So if this is our tree, or this is the regions, say this is the region. If I only have one data point here, in that region, I can't really be sure whether that was a randomly read one, or it is the actual class here. But if I have a lot of data points, then I can be more confident that we are doing the right decision by saying that this region, the true label is red crosses. Also, if it is too big, another problem is computational efficiency. If it is very large, the tree becomes computationally more difficult to construct and also evaluate. But maybe even more important is how interpretable the tree is. So here, this tree, the first tree at the top, this one is probably easier for humans to interpret. Suppose you constructed this tree and want to give it to a medical doctor, and in order to help him or her to make a better decision. If you give something that is very complex and complicated, the doctor may say that, well, I don't understand what is the reason behind this. But if it is simpler, then the doctor may say that, yes, okay, I understand what is happening here. And well, these values for a split, okay, this is based on data, but this is a meaningful split. So that's one of the reasons to prefer smaller trees. Okay, so this is, okay, so there is another concept that I want to talk about, which is related to this simplicity or complexity, which is called Occam's razor. Have you heard of Occam's razor in other courses? Okay, few people. Okay, perfect. So I can't remember when Occam was, but it was maybe 10th or 11th century around then. So he had this famous saying that, I'm just paraphrasing, that, okay, I can't really remember what he said. So, but it was along the line that if everything, we have an explanation for the same thing, we should prefer explanation for the same thing, we should prefer the simplest one. So this is Occam's razor. That says that, okay, here I'm writing it as find the simplest hypothesis that fits the observation. So it's kind of like a more modern version of it. So if you have, say, two trees, both of them explain your data equally well, which means that your training error in both of them is the same, like small number, then you should prefer the one that is simpler. But this is kind of interesting principle and useful principle, but it is not obvious how to formalize simplicity. And there are different ways to do it, actually. Like there are different ways that we can formalize simplicity in statistics and machine learning. People have talked about it a lot. But one of them that we talked about here was essentially the size of the tree. Smaller tree is simpler than a larger tree, but that's not the only way to formalize simplicity. Okay. A few other things that I want to talk about. I think I mentioned some of them, like a large tree can overfit the data. And the other issue that you have less and less data points at the lower levels of the tree, because at each split, you're basically halving your data, not exactly halving always, but the number of data points would be divided by something. So if you go depth 10, there wouldn't be enough data points at those nodes. As mentioned several times, greedy algorithms do not necessarily find the global optimum. Finding global optimum is a computationally expensive problem. Okay, for continuous attributes, split based on threshold and choose to maximize information gain. So this was essentially what we have been doing as a kind of running example. Our thresholds were continuous. There are other criteria used to measure the quality of splits. We talked about information gain, accuracy gain. The other one that is common is Gini index. So that's another criteria. One thing that I didn't really talk, but it's common in practice, and many packages do this, is pruning a tree. So many of these methods start constructing a tree, but then at the end starts to simplify the tree by removing some of the nodes. So for example, if your tree is like this, Okay, so it's kind of large tree. So you construct this tree, but then the pruning would come and says that, okay, let's remove these two, and then maybe remove these two, and make a simpler tree this way, based on some criteria. So, but we are not talking about that. Decision trees, I guess the other thing is that can be used for regression or real valued output. The usual criteria that we use there is not information gain, but it's more like a accuracy gain. So essentially we minimize the squared error, which you will, I guess you have seen previously, but we will see in next lecture a lot. So the criteria would be squared error, which has the same interpretation of accuracy. It's not classification accuracy, but accuracy in prediction of something. So yeah, I guess we can compare it with k-nearest neighborhood. The advantage of decision trees over KNN is that it is easy to work with discrete variables because it doesn't really matter whether the variables are continuous or discrete. For KNN, it's difficult because then you need to define distance between discrete variables, and defining distances in discrete over discrete variables is not as obvious as choosing, say, Euclidean distance.
Like why KNN is not correct, is correct?
Because because you need to define, so the question is that why KNN is not good for discrete value. And the reason is that the way I defined KNN was based on some distance, like Euclidean distance between two vectors. But if the values are, say, this takes discrete value. So for example, 0 or 1, for example, or 1, 2, 3, 4, 5, or anything like that, defining the distance between them would be not as obvious.
But the vector is discrete. It's, for example, like 1, 2, 4.
Yes.
The vector. So
no, well, 1, 2, 3, like your, yes, so vector is discrete, right? But what's the distance of, how do you define a distance of, maybe it would be, let me try to find an example that is less obvious. Say skin color, okay. Skin color, say you have 3, 4 different categories. How do you define the distance between, say, white and black on a skin color? It is not like, there are 2 different things. There is no distance like 2, and you can say that, say, what is the numerical value? Maybe another way is that so these are not necessarily vectors in a usual vector space. So we can't define distances the usual way. I mean, there are other ways that we can define distances, but it's less obvious. Okay, so you can easily deal with missing variables. So if you don't know a value of something, maybe because in your recording, you don't know, you didn't measure that value. For KNN, that would cause an error problem because then you have a point, you have a vector which and then you want to measure the distance. So it's vector 1, vector 2. I use prime here. And you know the value of this one. I guess this would be 4 and 5. So the distance between these 2 things would be a bit problematic because of, because of this term. Like, how do you measure distance between x3 prime and unknown value? You can try to impute it. You can try to say that if I don't know the value, I can consider as 0. But that's a bit questionable. But here for decision trees, you just consider this as another variable, say, with a binary variable, whether something is known or not known, and then deal with it that way. Okay, so the other thing is that it's robust to scale of inputs. So if you multiply inputs by 10, it doesn't change much because your decision point is you just need to decide where to do the splitting. And if you scale everything with the same value, it doesn't change anything in the procedure of splitting. But for KNN, which was reliant on the choice of distance, that scale changes the value of that metric or distance function use. Also, I think in practice, it's good when there are a lot of attributes, but only a few of them are important for making a decision. So that's another good property of it. But KNN can't easily deal with that because if you have a lot of variables, it just computes, it needs to compute the distances between them. And at least the basic way that they describe, you compute the Euclidean distance. You don't give special weight on certain dimensions. At test time, it is fast, and it is more interpretable compared to KN. I guess I talked about that. So advantages of KNN over decision trees. You can say that it can handle attributes features that interact in more complex ways because KNN basically divide the space, the way I describe it, divide the space to orthogonal dimensions, like look at only variable, width variable and height variable, but separately, not at the same time. But KNN has this ability to look at the combination of both of them. Also, KNN can incorporate interesting or useful distance measures. So if you have some prior information, what is a good distance here, something other than Euclidean distance, you can use that, incorporate that information for KNN, but you don't have that for decision trees. Okay, so as a summary, there are ways to make decision trees more powerful using a technique that is called bagging, bootstrap aggregation, which I'm going to talk about in a few lectures. But then if we do it, some of the good properties of decision trees would be lost, including the interpretability of it. And you see why. Yeah, so this is so far, we talked about two different methods of doing machine learning, KNN and decision trees, which to some may look like, okay, so I learned one method and then I learned another method. Next, I'm going to talk about a more modular approach that by basically we can design a lot of methods by changing each component of that whole system, each module of it. Yeah, that's all for now. Maybe we can have a break now, quick break. Now it's 28, maybe we start in 3 minutes. Or yeah, 32, let's start at 32.